The developer notices that method k has a bug and wants to remove it, along with every method it calls directly or indirectly, since those are all considered suspect. Given the list of which methods invoke which others, the task is to figure out this whole chain of suspicious methods and describe how to remove them from the project. One broken method just took down 3 others. Hey, I'm Kai. Welcome back to Fun with Learning Technology, the channel where we turn gnarly interview problems into things that actually click. Today we delete a bug and everything that depends on it without deleting the wrong thing. Let's go. Here's the setup. We've got n methods and method k is the one with the bug. The invocations list tells us who calls who. A pair A-B means method A calls method B. Our job is figuring out which methods have to go and which are safe. This isn't just a LeetCode party trick. Dependency graphs like this show up in build systems, package managers and microservices. One broken service and everything downstream that depends on it needs to go to. By the end of this, you'll spot this pattern instantly. Say we've got 5 methods and method 0 is the buggy one. The pairs are colon, Cali, so 1, 2 means method 1 calls method 2. Notice method 0 calls both 1 and 2 directly. Think of it like a phone tree, a list of who calls who, a checklist so you never recheck the same suspect twice, and a to-do pile of who's next. In code, that's a dictionary of lists for the call graph, a set, so checking if a method is already suspicious is instant, and a stack so we can warp the graph without Python's recursion limit biting us. Once we lay every pair out as an arrow, the structure jumps out. Method 0 points at 1 and 2, method 1 also points at 2, and 3 and 4 sit off on their own little island. First instinct, just delete method k. But that's too shallow. If k is buggy, it's been quietly corrupting everything it calls to. So what exactly needs to go with it? That's next. Here's the trick. First, suspicious means k plus everything k invokes. Directly or indirectly, that's forward reachability starting from k. In our graph, k is method 1 and 1 calls 2. So both 1 and 2 are suspicious. But look closer, method 3, which is completely healthy, calls straight into method 2. If we deleted the suspicious group now, method 3 would be calling into thin air. That's not allowed. In short, a group can only go if nothing healthy still depends on it. So after a group can only go if nothing healthy still depends on it. So after we find the suspicious set, we check every edge. If a healthy method points into that set, nobody gets removed, not even the bug. Reachable from k marks who's suspicious group now. Method 2 is deleted the suspicious group now. Method 3 would be calling into thin air. Picture starting a little flood fill at k. It spreads to everything k calls, then everything those methods call, and so on, until it stops finding new ground. Every method the flood touches gets marked suspicious. This part's just bookkeeping. For every caller, Kali pair, we append the Kali onto that caller's list. Now graph of k gives us exactly who k invokes directly. We seed the set and the stack with k. Then we pop a method, look at everything it calls, and if we haven't marked it yet, we mark it and push it on to check later. When the stack's empty, suspicious holds the whole infected group. Back to our 5 method example. We start at 0, mark it. 0 calls 2 and 1, mark both. 1 also calls 2, already marked. 3 and 4 never get touched since nothing points from the suspicious side out to them. Suspicious ends up being 0, 1, 2. Quick pause. 4 methods, k is 1. 1 calls 2, 0 calls 1, 3 calls 2. Suspicious is 1 and 2. Before I show you, what does this return? Think about who's calling into that group. Nothing gets removed. Method 0 isn't suspicious, but it calls method 1, which is. The moment we find one edge like that, we bail and return every method untouched. Otherwise, we just keep whoever's outside the suspicious set. Here's the whole thing in one place. Build a glove, flood out from k to find who's suspicious, check if anyone healthy calls in, and if not, hand back everyone who's left. Clean. 3 ways we build rip here. Skipping the incoming call check and always deleting the suspicious set even when it's blocked. Using plain recursion for the traversal, which can blow past Python's recursion limit on a long chain. And forgetting that k itself counts as suspicious, not just what it calls. You could write the traversal recursively instead of with a stack. Honestly, it reads a little cleaner. My honest take, I'd still skip it here. With n up to 100,000, a long chain of calls can blow past Python's recursion limit and crash. where the stack version just keeps looping. Every method and every edge gets looked at a small constant number of times. So it's big O of n plus the number of edges, both in time and in space. If k doesn't call anyone suspicious, it's just k alone, and it gets removed cleanly. With no invocations at all, nothing can block removal. And sometimes, when the graph loops back on itself, every single method turns out suspicious, we just return an empty list. Let's tie it back. Remember method 3 calling straight into a suspicious loop earlier? That's the entire problem in one edge. Find who the bug infects, then check if anyone healthy still calls in before you delete anything. The pattern that travels, whenever you're removing a connected group of nodes, don't just ask what's reachable from the source. Also ask what still points back in from outside. Want to take this further? Try it with more than one buggy method at once. Same idea, just multiple starting points. This algorithm took me years. Hitting subscribe takes 1 second. If something feels off or missing, or you want to see something new, tell me in the comments. Quick one. Method A is reachable from both the entry point and the buggy method. K, do we delete it? Pause and guess. Think about what happens to the rest of the app if you're wrong. Keep it. As long as the entry point can still reach it through some other path, it's still part of the real app. You only cut what K reaches exclusively. Round 2. With 100,000 methods and a dense edge list, is a plain BFS from K actually fast enough here? Count how many times you'd actually touch each node before you answer. Yes, easily. BFS touches every node and edge exactly once, so it's linear, not quadratic. No nested loops required.